So last time we talked about the Laplacian equation, Laplace u equals 0 in polar coordinates. And we all, had a unspoken agreement that we're going to accept that the Laplacian in polar coordinates looks like this because we don't want to go through this chain rule again. And I say again because you did it in a homework, specifically starting from this point where we assumed we have a function u of xy, and we've replaced the x coordinate with r cosine theta and the y coordinate here with r sine theta. And I fixed this typo that was here last time. There was the r was missing right here. So I fixed that. So yeah, we starting with this function in the homework 1, we did all of these partials and essentially arrived at this formula here. And so I've also laid out the details of the chain rule. And, of course, if you want to go through it, you should, but this is just this isn't about the chain rule. This is about solving PDEs, So now we want to start with the Laplace in polar form and talk about the boundary conditions. Remember, there's no initial conditions here. That Laplace u equal to 0 here. Remember, the Laplace is u partial xx plus u partial yy. Oh, it's down here. So remember, our Laplacian in rectangular coordinates is this equation, which we're setting equal to 0. There's no time variable. This is essentially a steady state calculation, but we're doing it in 2 dimensions. So here in the polar coordinates here, we have, there's this form for Laplace u equal to 0 in polar coordinates. And then there's this form, which is slightly more compact. And so what's going on here is if we do, so right here, there's a derivative that needs to be done. And here you would need a product rule. So if we did this product rule, so careful, you need a product rule, then you'd get the same equation that's over here. And so traditionally, typically what you'll see is it'll be written in this form in most of the literature, just I guess because it looks more complicated. I don't know. But that's your Laplace u equals 0. And so one thing that just from a math point of view, just like a Calc 1 math point of view, is we have a r in the denominator here. And so, of course, we now want to keep an eye on that and make sure, we don't let r equal 0, right? And here we have an r in the numerator. And so you say, well, what's wrong with that? We want to make sure r doesn't blow up to infinity, or we want to keep an eye on what happens if r goes to infinity. So now those are, starting to be are just straight up math technical issues, not necessarily any physical issues with the problem. So here you can imagine this is a steady state calculation for a heated, piece of metal with some type of circular geometry. We'll talk about the domain geometries here in 1 second. And here I just make a comment about the notation, and Haberman's book does use this notation. They write, I believe they write uxy equals ur theta, and that's technically incorrect. ur theta is just taking the function u and replacing x and y with r and theta. And that's not what we're doing here. This is not, that's not the polar form, u partial r plus u partial theta. That's not the polar form of u partial x plus u partial y, right? The chain rule shows us this is the correct form. So, all right, having said that, let's get to solving some PDEs, which is the main reason that we're here. So before I get to the PDEs, let's talk about some potential domains now. It's a 2D domain for polar coordinates, of course, is best suited for circular shaped domains, or, even if you have a domain like, if I had a domain something like, then you could break this problem up using the linearity we could break this problem up into two Laplace U problems. I could do a Laplace U here, and you'd have this type of domain right here. And that would be one problem. And then I'd have another, pose another Laplace problem here, say Laplace U equal to 0 here. And then we decompose the original problem into two problems. And I can use polar coordinates to solve it here and use whatever coordinates to sort this out. Maybe some have to figure out what's going on here. And then put the solutions together, if you want to now start talking about more weird shaped domains, but let's not get ahead of ourselves. So here, the starting point, I guess, is where you have it's inside the disk of radius r. So here we're just inside the disk. And so here, in terms of boundary conditions, we have a boundary here on the edge. Not the guitar player. So here, boundary condition on the edge. And so in terms of a heat situation, I'm very heat equation oriented. In terms of heat situation, you could say, okay, we've got some type of prescribed temperature on the edge here of this thin metal disk. And so now, we want to be able to find U. The U of xy will tell us the temperature at any point in space. So remember, time is not involved here, which is a little tricky because I think our brain naturally, parameterizes everything by time. Here, if you pick a physical spot on the disk, there's no weighting because time's not involved. It's just a constant temperature. The only temperature variation you would see is if you physically moved, because time is not a factor. Nothing is changing in time. The only thing here would be a temperature change if you physically changed your position. So here, we'll solve this problem today where we're inside the circular disk here. And we'll have a boundary condition on the edge, and we'll use separation of variables and all this kind of stuff. The opposite problem would be outside the disk. So here we have, we've got, I guess, this infinitely large metal plate, punch a hole in it, right? And so here we're outside, and there's a boundary. There's this boundary right here, which could have some temperature, prescribed temperature being applied to the boundary. But there's also another, unseen boundary, which is the horizon, the boundary at infinity. So here, if we, keep going out forever, it's that boundary to infinity and beyond. So here's an annulus. So actually, let me go back here. So one thing I wanted to mention is the issue. So here, yes, we have a boundary condition on the edge, a prescribed temperature on the edge. One issue is this includes r equals 0. So here, let me remind you of your polar coordinates. So remember, r is think of r like for the word ray, and think of this ray emanating from the center. The center here is called the pole. And so r it's a radius, it's a ray, it represents your distance from the center. And so in this case, and negative r would just go in the opposite direction. So in this case, we have r is between 0 and capital R. So here, we have to be careful about what happens, at least in limit to our solution. What happens to our solution U as R goes to 0? Because if you look at the polar coordinates version of Laplace U, we have an R in the denominator. And so just not even as a matter of physical concern. Physically, there may be nothing going on. Physically, for the metal disk, there's no issue at the center. But mathematically, there's an issue. And so, remember, we're trying to create a fake reality here. So yeah, so for the disk, we'll talk about how we handle that issue. for this case where we're outside, the origin is not an issue. So here r equal to 0 is not an issue, but now we have to worry about, well, what happens when r goes to infinity? So there we should say, okay, well, what's going on with that, as a matter of mathematical concern, right? So from that point of view, the annulus, I think is quote unquote the best shape. So for the annulus, we're outside, right? We're in between, we're in this donut shape, right? So here, let me finish putting in my lines here. So the red region is where we are not. All right. So for the annulus, we're inside this portion here. And to me, I say this is really nice because, well, we avoid the origin. So I mean, we avoid the pole here, r equal to 0 is not an issue. And we avoid the horizon. R going to infinity is not an issue. So, just from a purely mathematical point of view, knowing nothing about the problem at all, haven't even tried to solve it, just looking at the polar form of Laplace U, given that there's an r in the denominator and an r in the numerator, we would suspect this annulus would seem to give us kind of the most mathematically trouble-free solution. Anyway, so let's see what happens when we do the separation of variables. So here's another type of geometry. We refer to this as a wedge shape or a pie shape, and it's inside this region here. So let's start with the canonical problem here, the ground floor problem. We want to start with doing separation of variables in polar coordinates where the domain is inside this disk of radius r. You can see here the domain. Here at the end of the day, the PDE is always the same. The only thing that's going to change are, when I say boundary conditions, the boundary of what? The boundary of the domain. So when you talk about PDEs, it's after you get past which PDE are you working on, heat equation, Laplace equal to 0, wave equation, whatever. It really comes down to what's going on with your domain, what's happening on the boundaries of your domain, and if time is a variable, what's going on with the initial condition. Here, time's not a variable. Here, it's all about domain stuff, okay? So here, the domain I have, R goes from 0 to capital R, with capital R being a legitimate boundary. So R equal to capital R would be our actual boundary. R equal to 0 is a mathematical boundary, and we'll need to address that in our mathematical framework as we set up these equations to model this situation. Theta goes from minus pi to pi. So theta starts back here from minus pi, goes to 0, right? So minus pi goes through 0 to pi. And this is user's choice. So you might say, hey, why not 0 to 2 pi? You can do that. Why, you can pick any, you can pick any random angle you want, pick any random angle and go. If you, for whatever reason, go from here. If you want to do that, sure, no problem, So here, for now, I'll do minus pi to pi. And, because this is a slightly different type of separation of variables, you'll be asked to repeat this procedure in the homework, but with slightly different boundary values here on theta. So for the singular points, so-called singular points, for this case, for this closed disk, we're worried about R equal to 0. In a general setting, we might also be worried about R equal to infinity, but that's not something we worry about here for the closed disk, obviously. So the singular points here at R equal to 0, this is due to the coordinate system. It's not any physical issue that has to do with the heated metal plate. So, we do this a lot in applied math. We make certain quote unquote reasonable assumptions for physical reasons. And it's a nice thing in applied math is sometimes if you're legitimately mathematically stuck, a way to reanalyze the problem is to study the physical situation and find some new physical reasons that give you, a chance to make some additional reasonable assumptions that'll help you mathematically. Now, of course, you don't want to make too many assumptions, because then the problem becomes too easy and there's no point in solving a problem that's too easy. But of course, you don't want the problem to be too hard, because a problem that's too hard, you can't solve. So it's really, when you're doing research, it's really about finding that problem that's just that right level of difficulty. Anywho, I don't know what the hell I'm talking about. So for mathematical reasons, we make this assumption right here when r equals 0 because of these r's in the denominator. So can't have that. So we make this mathematical. And you say, well, why do you do that? Well, the standard line to throw out is physical reasons. It's reasonable. Evan.
Is there any physical situation where this would not be the case, or it would not be bounded in the middle?
I'm sure some Hollywood movie. I don't know. Let's think. Maybe the temperature would be blowing up at the origin, So something, maybe like with a jet plume, this would not be a good model. Or you just remove the boundedness assumption, I guess, if that isn't physically reasonable.
There's no time component of this problem, right?
There's no time component, that's true.
Okay, because I can imagine a scenario where it goes to infinity in time, but we don't have to consider that here.
That's true. So I'm being told from the mothership that this perhaps in black holes, something's going on at the center. Take a left turn at quantum entanglements, and once you get to black holes, go right. I don't know, but yeah, so maybe things that when gravity diverges, potentially, says Jacob. Oh, I guess you can all see it. I was trying to pretend like I knew something. I forget. You can all see the chat. Yeah, so Jacob says black holes where the gravity diverges, which is pretty fascinating, I gotta say. Black holes blow my mind. Okay, anyway, so periodicity conditions. So there are actually, due to the geometry, due to the geometry, if you look, this is going to be a true fact here. So what's the fact here? So first of all, let's fix r, fix some r, say r sub 0. And now if you just let theta vary for the fixed r, we get a circle like this. And now pick a point on that circle, aforementioned circle. So here I pick a point, and if you go around 2 pi at we'll be right back at the same point, right? So if I start here, go around 2 pi radians, I'm right back at the same point. So for geometry reasons, we have this periodicity. Here I say by periodicity. It's not by periodicity, it's by the geometry. And I'll fix that. It's the geometry gives us the periodicity assumption here. It's by the geometry. Sometimes a bit, is all right? It looks weird when your handwriting is totally crappy. Anywho, so there's your periodicity condition. And that's in general for theta. And the other thing we're worried about is right here at this kind of joining point where minus pi and pi, where they meet, the crossroads. Here, we want to make some assumptions, at least physically, about what's happening with the function. So now we want to worry physically what's going on with the temperature across this mathematical boundary that we've created that's from our coordinate system. And so, we assume both UR theta, the temperature, if you will, and here, U partial theta, you should think about what that is. That's the spatial change of the temperature in this radial, as you go around, right, a circle. We assume they're continuous, that the limit from the left and the right are equal. So limit from the left and the right with respect to pi. So we assume the limits are equal for physical reasons. And so that gives us these additional conditions. I mean, I don't know if you want to call them boundary conditions here. Pi is sort of an artificial mathematical boundary for the theta variable. And this right here, again, you know, if you think about the polar coordinate system, r equal to 0 is kind of a weird boundary at a, you know, infinity would be sort of a boundary of the coordinate system. So I don't know if you want to think of these as boundary conditions, but these are the additional assumptions we're going to make in addition to having the PDE here. And so we need one more final condition. We actually, it's a physical, you know, we're going to have what's the temperature when R equals capital R. So there's this boundary of our actual domain here when you're considering inside the disk. So here we still need to say, okay, when R equals capital R, what's U doing? So U of capital R theta, that's the other piece of information that we need. And this is a crucial piece of information. So now think like a Fourier series. When you want to figure out your coefficients, we always use some kind of initial condition or some kind of extra data on the boundary, right? So here, it's this data on this boundary that's going to allow us to find our initial condition, our coefficients in our Fourier series. Not initial conditions, there's no time here. So, by the way, we do have this vector space structure, it can be shown. So functions that satisfy both of these, the boundedness condition up here and the periodicity conditions at pi minus pi for, you know, the function and the partial with respect to theta, they form a vector space. So if any two of them do it, you add it, that'll also satisfy it. If a function satisfies these conditions multiplied by a scalar, that will also satisfy. So this is, you know, starting to set the stage for our separation of variables. So here's the PDE we want to solve. I write Laplace U equal to 0. Be careful. This is Laplace U written. That's not a typo. That's written in terms of Cartesian coordinates. But the actual PDE we look at will be the PDE that's in terms of R and theta. Okay. So here, that's why here I say, for now, here's the kind of a legitimate boundary condition, a legitimate physical boundary condition is the temperature at the edge of our circular disk. And I don't say initial temperature because time's not a factor. It's just the boundary condition, boundary temperature. That's the kind of, from a physical point of view, perhaps that's the only like legitimate boundary condition. Then we also have what we talked about due to the singularity at 0 of the coordinate system. We have this condition here. I don't know if you want to call that a boundary condition, but that's an additional assumption we have. And then due to the geometry and physical reasons, we have this continuity assumption at the boundary of the theta coordinate system, minus pi and pi. So there's this interplay of math and physical reasoning happening here. And so these equations all together here now, that forms our problem. So we've got the PDE, the temperature at the end, the boundedness condition, and this periodicity continuity condition. So that now is where we're starting. That's all the information we have, you know, and of course, you know, we have this domain here. So that's the starting point, okay? So let's try separation faux variables. Huh? So I'll fix that. So here it's not quite the same. I mean, the starting point's the same, but the squiggles are different. So here I assume u r theta can be written as a function of theta only times a function of r only, and that it's non-trivial. And so from the polar form of separation of variables, we can get these two equations. Okay, so I do it right here on the next slide. So hold on. Okay, so if you're like, wait, where did these equations come from? I do it on the next slide. So I'll show you in a second using the polar form of Laplace U and using the separation of variables assumption, we get an F equation and we get this G equation. And here the F equation is in terms of theta. And so these boundary conditions that have to do with theta, I'll show you here in a second, will give us these boundary conditions here that we see for the F equation. Okay, so I'll do the separation of variables explicitly here in 1 second. So the F equation, if you look, this is actually the same as the F equation for the standard heat equation on a ring. If you change the thetas to x's, then it's identical. So I'll refer you, think about heat equation on a ring where the ends are meeting. And so we assume both the heat flux and the temperature are continuous. So we set the endpoints. So you remember heat equation on a ring, you get the full Fourier series. If we do heat equation with Dirichlet, on a rod with Dirichlet boundary conditions, we get a sine series. If we do heat equation on a rod with insulated boundaries, Neumann boundary conditions, we get a Fourier cosine series. If we take the rod and use our brute applied math strength, make the rod into a ring, then we get these boundary conditions here where the temperature and heat flux have to be equal. And in this case, we get the full Fourier series as our solution to the F equation. So I'll let you review the heat equation on a ring to remind yourself of all those details, but it's the usual stuff, except instead of the variable being x, it's theta here. So here, because because we have pi in here, you can solve and show that lambda n is n squared. It's the usual, if you try and do it generically, you might get a form that's n pi over L squared, but here L is pi and things have canceled. And so I'll let you solve the F equation. This is nothing new. What is new is this G equation. We have not had a G equation like this in any of the separation of variables that we've done. So this is new. The F equation, as I said, we know from heat equation on a ring. Okay, so let's look at the G equation. For the G equation, in this particular case, we know lambda sub n equals n squared. Here, it's a similar trick, so the next question is, how do you solve this ODE? And it's a very similar trick. So typically, when it was just like first order and there wasn't like G double prime, we would say, assume the solution has the form e to the, I guess we used R before, so I can't use R anymore. We would say, assume the solution has the form e to the px, and then plug that in. So here we're going to do something similar to that, but we're going to assume the solution has the form r to the p, because there's this r squared in front here and this r right here. When we take two derivatives, that p will be a p to the minus p to the r to the p minus 2, and these terms will combine nicely. You can think of r to the p, it is a type of exponential term. It's e raised to the p ln of r. So it's almost like we're taking it, kind of viewing it from an ln perspective. So this equation, by the way, this equation is a total result of plugging in this assumption into the polar form of the PDE. And I didn't show those details, but it's not difficult. So, it's very like regular separation variables. So here, this U and this U, and maybe, in this case, it's better to use the fully expanded form. So pardon me, I'm going to go back to the fully expanded form here. Let me talk about just so how we start the separation. So starting with this equation, you set it equal to 0 on the other side. So hold on, let me do one of these deals here. Let me set it equal to 0 on the other side. So I just want to talk about how you start the separation of variables. It's not difficult, but just let me give you a picture of it. So these U's right here, replace these with F times G. So I'm going to replace that with F of R. Let me try that F again. I'm going to replace this with F of R times, sorry, not F of R, it's F of theta, my bad. F of theta times G of R. This is how the separation of variables starts. And a nice thing to do to simplify the whole equation is to multiply both sides by R squared. So multiply both sides by R squared, just to get rid of the R squared in the denominator. So I'll have 0 equals R squared, second partial of U with respect to R, plus R times the first partial of U with respect to R, plus the second partial of U with respect to theta. Then replace U tilde with F theta times G of R. And then separate the equation into, divide both sides by the F. You'll have F double prime times G of R. And so you can separate the equations in the traditional way and set it equal to negative lambda. So the homework will lay out some of those basic steps for you for how to start separation of variables. So once you do that, once you plug in the F of theta times G of R assumption into the polar form, you will get these equations, the F equation here and G equation. So the F equation is the same as in the heat equation of the ring. So that gives us the full Fourier series. For these particular boundary conditions, we get lambda n equals n squared. And so now let's solve the G equation. So for the G equation, as I mentioned, we make the assumption that G of R equals R to the P. So just see what happens, say, well, and you think about that's a type of exponential. So what happens now is I replace right here these capital G's, right? So G double prime, so the derivative of this G double prime is this right here. If you take the two derivatives of R to the P with respect to P, we use what's called the power rule. You bring the exponent down and subtract 1 from the exponent. So here we do it twice. So I get P times P minus 1 times R to the P minus 2. And you'll notice this R to the P minus 2 will multiply with the R squared that was in the front there. So that R squared comes from the polar form of the Laplacian equation. It was in the denominator, but we multiplied both sides by R squared and got it up in the numerator. That's where that R squared is coming from. And here we need a first derivative. Here I have a G prime of R. And so this is the G prime of R term. And it's being multiplied in the front by R. And that's from the PDE. That R again is coming from the PDE. You have a 1 over R term plus a 1 over R squared. So if you multiply both sides by R squared, you'll get that middle term will be multiplied by an R. And then finally here, we have just G of R without a derivative, which is our last term, but being multiplied by an n squared in the front. And that's from when we solved the F equation for the eigenvalue. Remember here, when we do separation of variables, we set everything equal to negative lambda, but then we solved for lambda. So now if you do the multiplication, so now here, if I combine this R squared with R to the P minus 2, R times R to the P minus 1, you get a common term. they all just become an R. And then an R to the P. So then you have an R to the P is this common term that we can factor out. So when you factor out the common term, what's left inside, here we have the P times P minus 1 is left, plus there's a P right here that's left, and this minus n squared. And so if you look at these things, that's exactly what we have, left in here. And there's the R to the P that we factored out. And so we assume R to the P is not 0. Why? Well, if R to the P is 0, G of R is 0, U is 0. We get a trivial solution, and that's one of our basic assumptions of separation of variables is no trivial solutions. So here, when you do the math here, this P distributes to each term. And so you get this negative P plus P cancel. So I get P squared minus n squared equal to 0. And here, if you factor this, this is P minus n times P plus n. And it's set equal to 0. So if you solve for it, you get P equals plus or minus n. So here I get P equals plus or minus n. You can factor it using difference of squares and then solve it. So for the n not equal to 0 case, so we assume n is not equal to 0 because you can show that when lambda is equal to 0, you get a trivial solution. So that's not even an eigenvalue, one step before. So here for the non-zero values of n, we get R1, which is, here our solution is R to the P. And so now we have two solutions. Here P has two possible values, plus or minus n. So here I've just replaced this R to the P here with n in one case and with minus n in the other case. And so this is a basis of our solutions. And so by superposition, this becomes, our general solution here for the G equation problem using superposition. Now be very careful. We're now going to use one of our conditions. Because here, keep in mind, this term is in the denominator. R to the minus n, that's 1 over R to the n. And so if R is equal to 0, that's a bad deal. So this part's a little bit, so a little bit subtle. Think about it now. R is in the denominator. We need our solution to be bounded at 0. 1 over R is not bounded. Here, 1 over R would blow up, So here, the boundedness assumption requires for the disk, for the closed disk, requires that C2 equals 0. Because the closed disk includes the pole. If you're on an annulus, the annulus does not include the pole. For the annulus, we would allow both C1 and C2 to be non-zero. But in this case, because we're in the closed disk, so here, remember, our domain is inside the disk. And the origin is a bad point. So, here we make C2 equals 0. But as I said, if you change the geometry, like on an annulus, both answers would be acceptable. So here's what our G equation solution looks like. So now we can do so here, if n equal to 0, why did I solve this? Interesting. I thought n equal to 0. I'll have to review this part. But apparently, let's just look at this. N equal to 0 does give us a solution, actually. I do remember this. So if n equal to 0, then R to the P is just 1. R to the P is just 1. So our equation is going to look like, so here I first do an algebra thing. Here I first divided both sides by R just to simplify it. And here I see what happens. It's if n is equal to 0, this term here disappears, right? That's why we need to consider n equal to 0. My bad. So here, if n equal to 0, this term that should be over here goes away completely. This term goes away completely. We're just left with this equation here. Yes, yeah, that's the thing. I always forget these little details, and that's why it's important to go through it. Evan?
So n equal to 0 wasn't an eigenvalue for the theta problem for f. So why are we considering it in this case?
I'm not sure. I'm gonna have to double check that. I'm gonna have to see, maybe is there a typo here? It's because in this case with the full Fourier series, yeah. In the full Fourier series, lambda equal to 0 actually is an eigenvalue. Because on the ring, when you have the full Fourier series, lambda equal to 0 is an eigenvalue. Because for the full Fourier series, you're going to get a constant term. So yeah, no, for the ring, lambda equal to 0 is an eigenvalue. So I was kind of assuming it wasn't, but I was getting a little ahead of myself. I think it's Friday syndrome, y'all. But Friday, math doesn't care about Friday, people. Write that down. It'll be on the test. So yeah, so lambda equal to 0 is an eigenvalue. Evan, thank you for asking that question. So lambda equal to 0 is an eigenvalue, so we should consider n equal to 0, and that's why these shenanigans are happening right here. And now let's be very deliberate here. What's the difference? This term is no longer there. Okay, so take a good look here. Let's really see what we're looking at. So how do we solve this? So here, as I said, we divided both sides by r. And now it's a little bit of math trickery. If you look at this long enough, you can write this as a product rule. If you look at it long enough, it's a little bit of math trickery. Let's work backwards. If we do the product rule on this, here you've got two functions, r times g prime, okay, calc 1 product rule, derivative of the first times the second. So here's the derivative of the first is a 1, times the second function is g prime of r, plus copy down the first, so here's r that I copied down, times the derivative of the second. The derivative of the second function is g prime, the derivative of g prime is g double prime. So this expression here can be rewritten as this r derivative of this product r times g prime. And you say, well, why do we do that? Well, now I can integrate both sides with respect to r. So now I can do fundamental theorem of calculus, integrate both sides, and get rid of this derivative. On the other side, we should get a constant. It equals a constant. So integrate both sides with respect to r. So here you just get your r g prime. On the other side, the integral of 0 is some constant. So now solve for g prime. So g prime is c1 over r. I just divided both sides by this r because I wanted to isolate g prime. I moved that over here. So you're dividing by r. Now we're integrating both sides with respect to r. On the one side, we'll get g of r. On the other side, we'll get the natural log function. So see, this is drastically different from the separation of variables, that we did in the traditional polar coordinates. I mean, Cartesian coordinates in x and y. So now again, for this domain, for the closed disk that includes the pole, the boundedness condition, if r goes to 0, we know ln is going to be unbounded. The boundedness condition that's a result of this closed circular disk domain requires we make c sub 1 equal to 0. So our solution to the g equation when, for n equal to 0 is just that it's a constant. Now let me emphasize, for example, in the annular region, in an annulus that doesn't equal 0 or infinity, right? Here, if we were in the region that didn't include the pole, but we would still include the horizon, you could still go out to infinity, natural log would still blow up going to infinity. So in an annulus where you don't have the pole and you don't have the horizon r going out to infinity, both here you can keep the natural log term if you're on an annulus. You know, on an annulus, the terms we would keep both these terms and we would keep these terms for the annulus superposition solution, you know. But anyway, I'll talk about the annulus in a second here. So I don't know why that's so weird. It's stopped the transition disappeared. Anyway, so as I say here, there's no restriction if you have a different domain. For example, if you're on an annulus, you know, and think about why that's true. So here's the product solution, folks. So let me do this one slide here and we'll have solved it, you know. So here's by superposition, when we do our product solution, we get something that looks like this. So let's take a look at the parts. So the cosine and the sine and even this lambda 0 are all coming from the F equation. The R to the N, this R to the N, and even this constant are coming from the G equation solution, and we've done superposition. And for a mathematically convenient solution, we divide this by capital R to the N, which is a constant. Why are we doing this? This will help us for the convergence analysis, which I'll do next time. We divide this and then we multiply this, A tilde, we multiply that by R to the N. And we call that new term, we call that A sub N. We call it, so that's what this is right here. And so if you cancel the capital R's, it gets you back to the original solution. So for the boundary conditions, if you let little r equal capital R, so that's where now this notation helps. If you let little r equal capital R, we get a Fourier series. And so now, you know, we're back to doing our usual Fourier series games that we know so well how to do. By orthogonality, I have a formula for the coefficients where, remember, f of theta is the given prescribed temperature on the boundary. It's the physical boundary of the disk, and it's the one kind of legitimate physical boundary condition we have. The other boundary conditions are more from the geometry and the coordinate system, you know. So that's our solution to the Laplace U in 2 dimensions when your boundary is a closed disk in polar coordinates. So this is the solution. This second form is really what we want to use down here. This is our solution with these are the formula how you find the coefficients. So I'm just about ended time. So you'll see on the homework, there's a Laplace U equal to 0 on a rectangular domain. You don't need to redo the separation of variables for that. And then you'll see there's Laplace U on a closed disk. And so you'll do a separation of variables and show the details and be very similar to what's done here. And then there's another domain, which is the annular region, and which we talked about, which I'll also talk about on Monday, which is in the notes and you can read ahead. The other result to finish up, which I'll finish up on Monday, and this doesn't show up on the homework, is this thing called the maximum principle, which this slide here is you know, motivating. This slide looks at the Laplace's equation in 1D and tries to get some intuition, you know. And so in 1D, we kind of get this simple situation, which I'll talk about on Monday. So let me stop right here. You know, I would ask you to review the separation of variables in polar coordinates, just what we've covered in these slides. And I would also wish you a great weekend and say be safe. And so I'm going to stop right here.